Hi, I'm Rahul Kannan. I'm a grad student at the Max Planck Institute for Astronomy, and today I'm going to talk about galaxy formation with local photoionization feedback. So as you have all heard during the course of this week, that so how do galaxies form? Gas cools in dark matter halos and then they form stars. But then if you simulate this, then gas cooling is too efficient, and then so you have a gas overcooling problem basically in simulations. So how they do it is, how they solve this problem in most of the simulations is to dump energy from stars or AGN from local sources by different methods. Of course, these methods do not work if you just do it because of the low resolution of the simulations. So you include a few tweaks, like you switch off cooling or hydrodynamics in order for the feedback to work effectively. So, but what the question I am asking is, are we calculating the gas cooling itself into the halos correctly? So there's this plot by Gnedin and Holon who show that the gas cooling is quite different depending upon the photoionization state of the gas. The cooling of gas not only depends upon the density and temperature, but also depends upon the photoionization state of all the elements in the gas. So if you look at just neutral gas, then the blue curve is the cooling rate. And if you look at fully ionized gas, then the red curve is the cooling rate. And you have like 2 orders of magnitude difference at particular temperatures in the gas cooling rate. Sebastiano Cantalupo, who's here, and Gnedin and Holon, they showed that this can have quite a big effect in galaxy formation. So now I look at ionizing sources that you can add in your simulations to mimic this effect, in order to see this effect. So the first one is the Hart and Maddow background, which is used in almost all simulations now to calculate cooling. But there are, of course, more sources of radiation in the galaxy itself. And the first one is the radiation from young O and B stars. They have UV flux, ionizing radiation. And what Cervinho 2002 in their paper, they showed that if you imagine that 5% of the mechanical energy of the supernovae is converted into thermal and cooled, then you get SED, this blue SED, which has a UV flux from the O and B stars convolved with the X-rays from the supernova X-rays, supernova shocks. That's one local radiation source that I use. The other one is post-AGB SARS, which was explained in quite detail by Charlie Conroy yesterday. And you can also use that SED. And so although the flux of this SED is very low per star, because they last very long, the cumulative effect of this SED can be quite important. So I include, in my simulations, as I'll show later, I include all 3 SEDs to calculate my cooling. Okay, so now just as a test case, if I put these SEDs into cloudy and it spits out the cooling curve, and you can see that the Hart and Maddow is in red, the post-AGB stars SED is in green, and the star formation rate, the cooling due to cooling in presence of star formation rate radiation field is in blue. And you can see at particular temperatures, even at relatively high metallicities, you can decrease the cooling by more than an order of magnitude. And this effect becomes quite important. So there are 2 effects you can see here. One is the reduction in the cooling rate. The other is the increase in the equilibrium temperature of the gas. So it goes from 4.2, 4.3, 4.4. And this means that a gas cooling from here under these conditions can only cool up to this temperature and no less. And so these 2 effects can be quite important. So in order to implement this into simulations, I use the gasoline code. I use some assumptions here. I assume that the escape fraction from new stars is just 5% at the Lyman limit frequencies. The old stars are considered as field stars, so you have a 100% escape fraction, and the rest of the gas is optically thin, so the flux goes as 1 by r squared. The other thing is I group radiation sources together, so my total flux is just the sum of the summation of the sources from here, and the distance r here is taken directly from the tree calculation. And if you want to find more about how we implemented it in the tree, you can look at this paper, which is in prep by Rory Woods. And there's also the third, that we use a non-equilibrium hydrogen helium solver plus an equilibrium metal which is taken from cloudy, and this follows the formalism by Sijing Shen and Vogelsberger. So now I implemented this in gasoline. If you want more information, you can talk to me. So I'll show you test particle results. So if you have, so now I just take one particle. I set its temperature to 2 times 10 power 5 Kelvin initially, and I evolve it with time under different radiation fields. So the Harton-Maddow is the blue, and then increasing star formation rates of 1, 10, and 100. And the flux is at a distance of 10 kiloparsec. So it's reduced by R squared. And you can see that, you can see that the increase in the cooling time and also the increase in the equilibrium temperature is non-negligible. You have quite a lot of increase in the cooling time. So the amount of time that it takes for the gas to reach its equilibrium temperature is quite high. While this cools in like 100 megayears, the Harton-Maddow, the other it takes almost like 300 megayears to cool to equilibrium temperatures. And that is basically because your neutral fraction is lower. So the bottom plot shows the neutral hydrogen and the neutral helium fractions, and you can see that the highest neutral fraction is for the Harton-Maddow case, and that's why you have a higher cooling rate. So 10 power minus 3. It is just test cases. I'll show you a full simulation. And it's the same with the old star. Oh, sorry. It's the same with old stars as well. You can do the same. This is just the new stars SED, and this is the old stars, the post-AGB stars. And you can see that you can also increase the cooling time, and increase the equilibrium temperature as well. So now I'll just show you the full implementation in a fully cosmological simulation, simulating a Milky Way type galaxy. These are the parameters of the galaxy. The important thing to note is we do 2 simulations, with one with only the Harton-Maddow UV background, and the other I'm using the Harton-Maddow background plus the local radiation sources, that is new stars and the post-AGB stars. So this is the star formation history. You can see that they are quite different after about redshift 1.5 or so, while the Harton-Maddow keeps increasing. While the run with only the UV background, the star formation rate keeps increasing. The star formation rate is quite constant, and it seems to regulate, the local radiation seems to regulate the star formation rate at a certain level, and this is quite consistent with analytical models that Sebastiano did in his paper. Now if you look at the rotation curves, you see the same difference. There's a huge bulge formed when you use only the UV background, whereas if you include the local radiation, then the rotation curves are quite, it's more slowly rising, and it makes quite a lot of difference here. To see why this is different, I'll show you the temperature density diagram, so in both the runs, and you can see clearly 2 things from here. First, this part here, the low temperature gas, is totally non-existent when you include local radiation. This means that you're creating some very highly ionized Strontian spheres in which the gas really cannot cool, and so you're creating pressure support to the disk. And the other important point is that the area in between the halo and the disk is less strongly populated in the run with local ionizing radiation. That's because you do not allow the gas to cool. Your cooling rate is really high. And this shows the column density map, and you can see clearly that you ionize everything, so the H1 column density in the large scale structure of the H1 column density is also quite different. Okay, and this plot shows the baryonic disk mass as a function of time. And so if you take the slope of this plot, then you will get the gas accretion rate onto the disk to first order. And so you can see that the slopes are also quite different. That means the gas accretion itself is stopped when you include these local sources of radiation. So to conclude, so it's a new method to put a local photoionizing radiation field in cosmological simulations. You get a 67% reduction in star formation rate, almost 40% reduction in the total stellar mass of the galaxy. You get slowly rising rotation curves. And this is because you have this kind of preventive feedback which reduces gas accretion onto the disk, and does also have this feedback on the disk, which creates pressure support in the disk so as to stop star formation. And so this is my take-home message. It says that local ionizing radiation is clearly very, very important and should be included in models of galaxy formation. Thank you.
All your gases at all your gases at 10 to the 4, right? You never get a cold phase.
Yeah.
In photoionization.
Yes.
Doesn't that worry you?
No, it does not worry me because I have.
Must be self-shielding.
Exactly.
In the disk.
Yes.
But you haven't put that in.
No. So the
so
first.
if you put it in, self-shielding, then of course your star formation rate is going to go back to where it was.
No, it won't go back because your self-shielding works only in the disk. I'm reducing the gas accretion onto the disk,
That's right.
and that effect is will still stay. Yes, I'm not. So that effect will still be important, quite important.
Daniel, did we already put that in your photoionization? Most of them,
Yeah, but you put only. Yes, you put only O and B stars, which means that you cannot ionize metals. At later times, it will be quite difficult for your SED to ionize metals, and yours is quite local, but I propagate my radiation throughout the volume.
I noticed some recent observational papers suggesting Milky Way size halos have star formation rate actually decreasing with time in recent history, but I haven't seen any hydro simulations show that sort of trend. Do you have any thoughts on that?
So as I said, I'm not telling you that my parameters match the Milky Way. I'm just showing you my effect on a Milky Way type galaxy. I'm not trying to match the Milky Way. I'm just showing you that this effect is quite important on Milky Way mass galaxies. So I can do a parameter study, of course, and then it'll come later. But now I'm just showing you that if you include radiation field from local sources, it's quite important and it can reduce the star formation quite a lot.